Hi everybody, so we're doing 13.5 today, the potential divider. I've got a little thing for you to think about at the start. Hopefully you'll be able to answer this by the end. When the pedestrian enters the sensing area, the brightness is 100% brown. So 30%, pedestrian enters 100%. So hopefully by the end you'll know how these fancy streetlights work. Big question, how do you create an automatic circuit? 13.5 potential divider circuits. Bronze, be able to describe the setup of a potential divider circuit and describe some of their uses. Let me just change that. Be able to explain how a variable potential difference could be supplied by a battery and explain mathematically how sensor circuits can be used. So let's look at the theory of the potential divider. A potential divider sounds really difficult, and over the years my students have got confused with them. It's just literally a circuit that divides your voltage or your potential difference. So all you need is two or more resistors in series. So it's literally just a series circuit with two or more resistors in it, because those resistors will share the potential or the voltage. Now, if you want a potential divider circuit that supplies a fixed potential difference, you need a circuit that looks like this. So you have a source of EMF, your series circuit with your two resistors in series, which will share this EMF. And then here you can attach a voltmeter or another circuit across one of the resistors. So if you have a look, because each of these resistors have a fixed resistance, the potential difference across each will not be changed. For example, if they were both 10 ohms and this was 10 volts, they would have 5 volts each because they would share it equally. And the voltage here would always be 5. So if you attached a circuit to this, okay, it would be supplied with a constant potential difference. If you attached a bulb to this, it would always have 5 volts. So the total resistance of this circuit is R1 plus R2. The current through the resistors, so the total current is a series circuit, ignore this section, it's a series circuit, the current's the same, so it'll be the terminal PD, so what comes out of the battery, taking off if there was an internal resistor, and then the total resistance. So you've got the terminal PD divided by the total resistance, and because the total resistance is R1 plus R2, this is the equation we end up with. Let's look at resistor 1. So we're going to work out the resistance of resistor 1. So we're going to use V equals IR. So the potential difference across resistor 1, V1, is equal to the total current, because the current is the same all the way around the circuit, times the resistance of 1. So we know that the total current is equal to this term here. So we're going to sub this in to here, and we get that times R1, which is here. Just making it look a bit neater, it looks like this. This is called the potential divider circuit. It's actually written a lot better like this. So the potential difference across 1 is equal to the ratio of R1 over the total resistance, R1 plus R2, times the terminal potential difference, or the potential difference that you get from the power supply here. Okay. Exactly the same for potential resistor 2. V2 is equal to the current, which is the same, times resistance 2. Substitute that equation in for current. You get this with R2. Make it look a bit neater, but actually looks a lot better like this. So this is telling you that the potential difference across R2 will be equal to the resistance of R2 over the total resistance times the EMF, or the terminal PD. These are known as the potential divider equations, and they're really, really, really useful. Let's say you want to provide a variable potential difference here, so you don't want it to be fixed. You'll need to create a similar circuit but have slightly different resistors. So you need to connect your source potential difference to a length of wire with a fixed resistance per unit length. So rather than having a fixed resistance, you would have a resistance that can change, but it has a fixed amount per unit of length. So it might be like 10 ohms for every meter. And then you can use a sliding contact, can be moved along the wire. You've probably seen one of these when we've done our circuits. We call them rheostats, so we've used one of these before, but you can get circular ones as well. Yeah, basically they're used for audio control. So if you're in a car, the volume control is one of these in here. It's just the length of the wire. Okay, or a dimmer switch on a bulb. So here's the setup you've got. You've got an EMF, and here's your rheostat. This one is easier to think about here. And then you connect your external circuit in parallel to that. And then as you move the slide contact here, you will get various amounts of potential difference, because what it does is it splits the rheostat in two. So you would have here, you've got this resistor here, this resistance, okay, in series then with whatever resistance is left over, because the current in this part of the circuit has to go through the whole thing. But the contact you're taking part, you're making the resistance different here. This is a really good setup because it varies the resistance of the bulb from 0 with the bulb off, if it was here, to a maximum here, which would give you full brightness. If you had a slightly different setup where you put the bulb in series with the variable resistor, you could change the brightness of the bulb because you can make this resistance high or low, but there would always be a potential difference across here because they're in series, and so it would always be slightly on. So this circuit is much better, and sometimes questions ask you about why that is. It's because in this circuit, the resistance across the variable resistor, across the bulb can be from 0 to a maximum. But in this one, they will always have a share of the potential difference. So it will always have be on. Okay, so that is how you supply variable PD. You can then have a sensor circuit which uses the same ideas. So example would be a thermistor, which you've come across at GCSE. So this sensor circuit produces a variable potential difference output which changes as a result of a change in physical variable, such as temperature or light intensity. So a thermistor will respond to the temperature of the environment. Here's our circuit with the setup. So you've got a source of EMF, no internal resistance. You have your thermistor here, and in this case you have a voltmeter in parallel, but you can attach an external circuit here because you could put a bulb here if you wanted to. And then here you've got a variable resistor. Now thermistors, the ones that we talk about, are known as NTC, and that stands for negative temperature coefficient thermistors. And this question gets asked all the time. What they do is they decrease their resistance when the temperature increases. So whatever the temperature does, the resistance does the opposite. This is basically because they're semiconductors. So when the temperature is increased, you release charge carriers from the lattice of the material, and that allows current to flow. So the energy from the temperature of the environment will increase the number of charge carriers in the material, which is interesting. So let's look what they do. Let's say there's an increase in temperature in this circuit. The resistance of this thermistor will decrease. The current in the circuit will therefore increase because you've reduced the total resistance, because these are in series. You've made this one smaller, so now there is less resistance. So the current in the circuit increases. The potential difference across the thermistor will decrease because it's got a lower resistance. It's not as difficult for the current to flow through it, so it won't have to give, the electrons don't have to give up as much energy to get through. So the potential difference across this thermistor decreases. But because you have a fixed amount here, and if you think about the hills from the previous video, if this is 10 volts, and the potential difference across here has gone down from 5 to 2, then this one will have to go up from 5 to 8 to still make 10. So the potential difference across the other resistor will increase. If we do the opposite, if we decrease the temperature, the resistance of the thermistor increases, the current in the circuit decreases, you've made this resistance bigger, and so the total resistance is now bigger, so you have less current. The potential difference across the thermistor increases, so its resistance is increased, so it's harder for the electrons to flow through, so they have to give up more energy. And therefore the potential difference across this one will reduce, so that they both still add together to make the EMF of the power supply. If you apply a secondary circuit here, if you apply it across the thermistor, that will turn on when the temperature gets cold, because what you need is enough potential difference across it for this circuit to turn on. And that happens, we want this one. When the potential difference across the thermistor increases, you need it to be high enough for there to be a big PD across it. So if you attach a secondary circuit across here, then when the temperature gets cold, the potential difference across the thermistor will increase and this circuit will turn on. So that's really helpful in heating the system in the house. If the temperature decreases, your circuit turns on. If you move this circuit here, the secondary circuit, and put it across this one, then you have a really helpful circuit because this will turn on when the temperature is too hot. So the potential difference across the thermistor decreases, so this one has less potential difference, so this one gets more, and then your external circuit turns on. So this is really helpful in a fridge or an air conditioning unit or something like that. The other sensor circuit you need to know about are LDRs, light dependent resistors. They do exactly the same as thermistors, but they work on light. So an LDR is used to control a circuit depending on the light intensity of the environment. LDRs decrease in resistance when light intensity increases. So they have that negative aspect again. They work using the photoelectric effect. So when photons of enough energy fall on the LDR, then electrons are emitted and can flow around the circuit. So if there's more intensity, there's more electrons emitted and you have a greater current. These look exactly the same as before. Light intensity increases, resistance of the LDR decreases, which leads to an increase in the current. The potential difference across the LDR decreases because its resistance is decreased, and so therefore the other resistance potential difference has to increase. And then you have exactly the same happening the opposite way around when the light intensity decreases. So these circuits are really useful. Again, if you put a secondary circuit here where it is in the diagram, it will turn on when it gets dark because the resistance is increased, so the potential difference is increased. So that's really good for an automatic street light. And then if you move this external circuit and put it here, that's really good if you want something to turn on when it's bright. Okay. So that's really good if you want like automatic shutters. Say it's really, really bright outside and you have automatic shutters on your windows, then they will turn on when it's really bright. Okay. This is a really helpful video to watch if you want to have a look about writing out the potential divider circuit. And then again, I want you to do the questions. So you can self-assess these next time, and then you'll upload a photo of them when they're self-assessed to prove you've done the work. And then for this piece of work, you should be self-assessing 13.4 questions and uploading your answers to those to check that you understood them. Okay. Any questions? Let me know.